Hello, am I audible and are you able to see the screen, the slide?
Yes, sir.
Okay.
Yes, sir.
I think not many people are going to join today. We'll wait for just one more minute and then we will start.
Sir, I had a question. So
Yeah,
there was this uh,
yes, please go on.
um, yeah, sampling of groundwater done in a place,
Okay,
and the values from hardness using titration, it was different from the value of hardness which was calculated by calcium and magnesium ion concentrations. There is two ways of calculating, right? Hardness. You
yeah,
can use it. Yeah. So what do you infer from it? Like,
no, like
if the
calcium and magnesium are so like you did it by IC.
calcium and yes, ion chromatography, like you have this calcium and magnesium ions, you get it, and then you multiply it by 2.5, calcium by 2.5 and magnesium with
Okay,
4.10, and you get hardness that way. Or you do it in the lab by titration, right?
so
Hardness.
in lab by titration we do the total hardness and we can do the calcium hardness, and by
Yes,
subtracting it we get the magnesium hardness.
yes.
Okay, but for from the IC, uh, ideally it should be the same because no, in IC, what did you say in the 2.5 and 4.5? What I didn't understand.
No, that's just the formula for calculating the calcium and magnesium hardness from the ions.
From the ions, uh,
Yeah.
what is how did you come up with the factor? With what factor is this?
So the factor is like calcium hardness, like using the molar mass of calcium carbonate, like um, calcium carbonate molar mass by molar mass of calcium, which is 100 divided by 40, which gives you 2.5.
Oh, okay, okay. You are converting. Okay, so like in terms of mg per liter as CSO3, you are saying.
Yes, yes,
Yeah. So see. In titration also you have to convert into in mg per liter as CSO3. See, IC is different. What you are saying is you are just converting it.
yeah.
No, like I am still not getting your problem because ideally by your titration test and your IC, did you do IC for the ions?
Yes, the values show, like, they're a set of parameters, and I think IC was done to calculate calcium and
Okay,
magnesium
so
ion.
ultimately you just converted into milligram per liter as CSO3. And that
Yes,
titration value also, did you convert into milligram per liter as CSO3?
I think I did, but let me check once and then.
Yeah,
Okay, if
because
that
yeah,
might be a mistake.
yeah. Ideally, both has to be because whatever formula you are using, you have to check
Yeah.
after titration also. It won't
Okay.
give you directly the result. You have to because always we report in terms of milligram per liter as CSO3.
Okay.
If you are
Okay.
calculating in terms of ion, then that is different. So you check in
So
both the cases in what terms you are representing it.
okay. So for titration, you calculate total hardness and calcium hardness, and from the total hardness, you subtract the calcium hardness to get the magnesium hardness.
Yes,
Correct? Oh,
yes. So whatever the
okay.
burette reading you must be getting, okay,
Yeah.
then we generally report in milligram per liter as COCO3. Okay,
Yes.
so you should check if you are making that conversion or not.
Yeah.
Okay,
Maybe that there could be a mistake. Yeah.
yes,
Okay.
but many a times it may happen that your titration values and your IC values may not match properly
Yeah.
because this IC is very sensitive. Okay,
Oh, okay.
IC is
Okay.
very sensitive and mostly IC will should only give you the accurate results. So
Okay.
what you should do,
Yeah.
you prepare a standard. Okay, you
Okay.
prepare some 100 milligram per liter of calcium or 100 milligram of liter of magnesium and you test it in IC along with your samples. and check if your
Ah,
known sample is giving the correct result.
okay. Understood.
Yeah. Then you can
Okay.
verify whether your samples are also giving the correct value or not. Because
Sure, sir.
titration you might not be sure, but in
Sure, sir.
IC you, because many a times you might have done some mistake in the calibration or something. So you check
Right,
one
sir.
of the standard. Okay, like that.
Sure, sir. Okay. Thank you, sir.
Yeah.
Thank you.
Yeah. So welcome everyone. We were having a small discussions. So let's start with today's class. So we are in week 7 now. So today we'll be looking at the question answers related to the contents of week 7. And you as all know, the name of the course is Water and Wastewater Treatment, which is taken by Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at Madras, where I am pursuing my PhD in environmental engineering. So let us quickly have an overview of the contents of week 7. So in the previous 6 weeks, we have seen all the concepts related to the wastewater treatment. Okay, so now we are moving into the concepts of water treatment. Okay, so in the following 6 sessions, we will be solving problems related to water treatment. Okay, so we started off by learning what do you mean by water demand. Okay, what are the different sources of water, how to determine okay how much water will be required for a community, what are the demand periods of various water and wastewater treatment structures, and for this demand how to do the population forecasting. Okay, and then we looked into the water quality parameters, so physical, chemical, biological, all these quality parameters that we have seen and discussed in detail. And then we started with the different units of water treatment. Okay, so what are the different unit processes or unit operations for this water treatment, and what should be what are the different characteristics of particles to be removed. Okay, what are the unit operations of surface water treatment. Okay, what are the electric charges and also basic info regarding that. And then we looked into the physico chemical treatment, starting with the coagulation. What are the different types of coagulants? Okay, what do you mean by double layer suppression, adsorption, and charge neutralization, and various other mechanisms of coagulants. So today we'll be focusing on the MCQs related to only these concepts. Okay, so let us now quickly move on to the first problem. It says that match list 1, that is delta P, with most probable option in list 2. Okay, for the population forecasting methods. And here delta P represents the change in population between 2 decades. Okay, so let's say 2021 to 2011, what is the change in population is determined by delta P1. Then 2031 to 21, it will be delta P2. 2041 to 31 will be delta P3. So they have given some relation between these change in population. You have to guess what kind of population forecasting method supports the kind of relation shown. So any idea? See, okay. Uh, the first question is like when we do any kind of population forecasting, what do we like? How do we select the method? Any idea how do we select the method for population forecasting for an area? What is the
Uh,
criteria of? Yeah, yeah. Please go on.
by by uh, by knowing uh, how much population is there in the previous years, like how many do we have, and then
Okay, yeah. So that means we see the trend in the growth or the decrease in the population. We generally see the trend of the past decades and we try to predict what will be there in the future. Okay, based on the uh, based on the demographics or based on the kinds of resources that are present in the city. Suppose it is a very uh, a new city with various opportunities for industries and for urbanization, then we know that this city is going to grow in the future. So then that time we will use some method which will give us a higher estimate of the population. Okay, whereas if it is a very old city which has already reached a saturation, where in the previous years there is not much growth in the population, then we say that okay, it has reached saturation, so then we will use some method such that it doesn't overestimate. Okay, so here also let's see, let's take up a case where it is in 2001, 2011 and 2021. First, there is 1 lakh population, then there is 1.2 lakh population, then there is 1.4 lakh population. So we can see that each decade the growth is around zero point 0.2 lakhs, right? And it is a constant. Okay, so whenever, so this 0.2 lakh is my delta P, the change in population. So whenever the change in population is almost equal in each of the decade, we generally go for the arithmetic mean method. Because if you see the formula, what is the arithmetic mean formula? What is the population of the last decade plus how much decades forward you are going, so n into the average population increase, right? Average population increase, let's say small p. So like that we, so this average population increase is nothing but whatever, like how much ever growth is happening per decade. So if it is a kind of constant, it is not growing by much, then we will use the arithmetic mean method. Whereas if this increase, okay, is like, let us go back to the relation. If this increase is higher every other decade, okay, like in case 3, p1 is less than delta p2, which is less than delta p3, so that means in the recent years the increase has been higher. So that time we will try to overestimate it or go for a higher value, so we will go for a geometric increase method. Okay, whereas if we don't know whether, if there is a not a clear trend between the increase within the decades, then we will go for the incremental increase method. Okay, is it clear?
Yes, sir.
Okay, so that's how, even if you see the formula also, so for a given set of values of the decadal increase, the arithmetic mean method will give you the least value. The geometric increase method will give you the maximum value, and incremental increase method will give you some value in between. Okay, so that is the way. If we will solve one question later, so you will be understanding it in a much better way. So here the correct answer will be option A. So one represents, that is equal increase in each decade, means arithmetic increase method. If the increase is increasing or decreasing, whatever is happening, we will go for some incremental increase method. And if it is a perfectly increasing decadal growth, then we will go for a geometric increase method. Okay, so that's how you have to do it. Let's move on to the next problem. Select the correct option regarding statements below. Statement 1 says ionic strength increases with charge of coagulant. Statement 2, electronic double layer thickness decreases by increasing coagulant dose till a certain limit, till a certain limiting concentration, and increases with excessive dosages. So tell me which of the statements are correct. So this is something related to coagulation. We'll discuss anyhow. Just, but please try to answer whatever you feel like is the correct option. So anyone knows what is like the formula or how do we calculate the ionic strength? Like what
So
does
I think A.
A? Okay. So let's
Ionic strength is equal to zero point 0.5 into sum of the z square, sum of
it is actually
zeta.
C into Z square. Okay. So concentration into the charge square. Okay, like that's how we denote. So if we increase the charge, what will happen? The ionic strength will definitely increase. Okay, because half Ci into Zi square. Okay, yeah, Preeti, it is correct. So option D is, I think, correct. Both statements 1 and 2 are right. And coming back to the second problem, what happens? It says that the electronic double layer thickness decreases by increasing the coagulant dose till a certain limiting concentration and then increases with excessive doses. So what we do is, suppose we have some pollutant which we want to remove of negative charge. So of we will add some coagulant to neutralize it. So what will happen? The negative charges over the particle will get neutralized, okay, with the coagulant's positive charge. Okay, so by this what will happen? The electric double layer will, the thickness of the electric double layer will be getting decreased because the charges are getting neutralized. But after a certain dosage, what will happen? Suppose all the negative charge are now neutralized. Now still you are adding more and more positive charge. What will happen? Again, the positive charges will be coming onto the system and it will start again the electronic repulsion. Okay, so it will again destabilize again. Okay, so by that way, the thickness of the electric double layer will start increasing. So that is why only up to a certain particular dosage, the thickness of the double layer will decrease and then it will start increasing again. Okay, we will see one figure later in one of the question, like how does it happen. But I hope you are able to understand. Is it fine or should I draw and make you understand?
Maybe later.
Okay, okay, we
Yeah.
will solve that problem and we will see. So just try to remember, like we have any particle, okay, over which we have some negative charges. It is a negatively charged particle. We add some positive charged coagulant. So it will try to neutralize the all the charges. But after a certain point of time, when all the charge is already neutralized, if we add more positive coagulant, it will again become positively charged and the electronic double layer thickness will increase. So that is the idea behind it. Okay, let's go to the next problem then. Particle entrapment in the precipitates during the coagulation called, so it is one of the mechanism of coagulation. Yes, that is the correct answer. It is called as sweep coagulation. So what happens in sweep coagulation is that the coagulant hydrolyzes to form some precipitates. Okay, like some metal oxides of AlOH thrice or FeOH thrice, and these amorphous precipitates will try to capture all the suspended particles as they settle. Okay, and this generally happens when the coagulants are added at a very high dosage. Okay, so it is a sweeping action. Okay, like with the help of a sweeping action, it will try to capture all the particles in the system with the settlement of the precipitate, right? So this will help in removing the particles from the water. So the correct answer is sweep coagulation. Next, okay, yeah. So here you can see the formation of electric double layer. So here they have marked something as X, Y, and Z. So you have to tell me what do they represent. So look at the options and let me know the correct answer. So we have a negatively charged particle, okay, and over which we have some charge accumulation. So we can see the stern layer and the stern plane. We can also see, actually it should be the thing which is marked as diffused layer, it should be diffuse plane. Then we have something as y and z and something as x. So x should be very easy. Okay, x should be very easy because it is marking something related to the potential. We have a plot between the electric potential and the distance. Okay, so that particular potential is called the zeta potential. Okay, that is called the zeta potential. What about y? Y is the combination of the Stern layer and the diffuse layer. Okay, y is the combination of the Stern layer and the diffuse layer. So it is called as the electrical double layer. So two layers are there, so electrical double layer. And then Z. So apart from the Stern layer, we have a diffuse layer. So Z represents the diffuse layer. Okay, so this is very direct. So here you can see if we have a negatively charged particle, okay, this is the negative, these are the negative charges. We are adding some more positive charges. So it is coming and getting accumulated and trying to neutralize the negative charge. Okay, because if more and more negative charge particles are there, they will repel each other and they will never settle. So we try to destabilize it. So only up to a certain point the electric double layer thickness will decrease, but if we add more and more positive charge, then again the particle become positively charged, and again the electrostatic repulsion will happen and the electronic double layer will increase. So yeah, so here I have given the definition of all these layers. So you don't have to memorize all these things. Just know that electrical double layer comprises of two layers. One is the Stern layer and one is the diffuse layer. So Stern layer is the compact immobile layer which is directly absorbed onto the charged surface. So the one which is near to the charged surface of the particle is called the Stern layer, whereas the diffuse layer is the one which is of more dispersed kind. Okay, it is the contact between the bulk solution and the Stern layer. So that is the diffuse layer. And zeta potential, it is the potential between the boundary of the charged particles and its surrounded liquid. Okay, so that is called as the zeta potential. Next, for a city of 6 lakh population, compute the fire demand in liter per minute using the Kitchling's formula. So I hope you know the Kitchling's formula. So for a city of 6 lakh population, what will be the fire demand? It's a one line answer. Please try to answer the correct value. 77942. Yes, that is the correct answer. 77942. So how did we get this? So, so as per the Kitchling's formula, the fire demand is 3182 root P. So here P denotes the population. Okay, but one thing that you have to keep in mind is this population in thousands. We have to report the population in thousands. So if we have population of around how much, 6 lakhs, or 6 followed by 5 zeros, so P will be equal to 600. So 600,000. Okay, so this small change you have to make. You cannot directly put 6 lakh in this. If you put, the answer will be wrong. So 3182 root over 600. So that is 77942 liters per minute. And since it's a empirical formula, so you have to memorize the unit also. Okay, here by looking at the formula, it may feel like there should not be any unit because population is in thousands, but since it's an empirical formula, it is in liters per minute. And always convert it into thousands because most of the fire demands generally deal with the population in thousands. There is one more formula. We will see it. Okay. Okay. So now here is a population forecasting method question. So the population of 2041 needs to be estimated by all this method. So we'll try to calculate one by one. So let us start first with the arithmetic increase method. So please try to answer. Take some time and try to answer what will be the value for the population in 2041 by arithmetic increase method. I'll wait for a minute. Yes, that is correct. 157,449. So let's see how to solve this problem for others. So this is question number, I think, 6. Yeah. So we have the population of each year: 1961, 71, 81, 91, and 2001. And we have the population also. So it is 6848, 13308, 36747, 58242, and 82149. So first, for the arithmetic increase method, you have to find out the change in population, that is delta P. So we'll simply subtract 13308 minus 6848. So for this, it will be 6460. Then for 81 and 71, we have to subtract. We will get 2349439. Then we will get 21495. And at last, we will get 23907. So once we get the change in the increase of the population, we will simply add them. Okay, we will find the sum of all this. So sum will be 75301, and after finding the sum, we will also calculate the average. We'll also calculate the average. So average will be around 18825. 18825. So once we get all this value, so the population in 2041 by arithmetic increase method will be equal to the population in the uh, final decade will be 2 82149 plus how many decades forward? We are going 4 decades forward. So it will be 4 into the average. So 18825. So this will be 157449. Okay. So similarly, did you find the answer for geometric increase? Anyone? So this was for the arithmetic increase. What we have to find for the geometric increase? We have to find out what is the percentage change in population. Okay. What is the percentage change in the population? So we will just divide the delta P with the previous year population, previous decade population. Okay. So it will be 6460 divided by 6848. So it will be 0.943. Similarly, for other decades, it will be 1.761. Then it will be 0.585. Then it will be 0.410. Okay. So now, after finding the percentage increase of population in each decade, we have to find out the geometric mean. We have to find out the geometric mean. That will be equal to 0.795. I hope you know how to find out the geometric mean. We have to multiply all the values and then take it to the power of 1 by n. Okay, so that is the geometric mean. So 0.795. Then the population at 2041 by geometric increase method will be the population of last decade into 1 plus the geometric mean 0.795 to the power of decades, number of decades we are going forward. So it will be 852,331. 852,331. So this is the geometric increase method. Okay. And then last is the incremental increase. So what we have to find out in incremental increase? So here we will find out what is the change in population. Okay. So we will just subtract these two. Okay, like this. So we will get some three values. So we will subtract the change in the population. So for first we will get it as 16979. Then, so this incremental increase can be positive or negative. Okay, there might be change in population increase or change in population decrease. Okay, so we have to take it as it is. So this is minus 1944 and then we will get 2412. So incremental increase we got. So here also we will first calculate the total, that is the sum. So that will be 17447 and then we will also calculate the average. So this will be 5816. Okay, so sum and average we will calculate and don't neglect the negative sign. Take it as it is. So P of 2041 with incremental increase, it is like first write the formula of the geometric increase, same, whatever geometric increase you have taken, same, then add what, n into n plus 1 by 2. Okay, so 4 into 4 plus 1 by 2 into the average of the incremental increase. So that is 5816. So we will get something around 215607. Okay. So with the same data, you can predict the population in three different ways. So here you can see the value of the geometric increase is the highest, followed by the incremental increase, followed by the arithmetic increase. So mostly for very fast growing new city, we will use the geometric increase because it will give a overestimated values. Whereas for a very stabilized city, okay, which is growing with the same rate, we will go for the arithmetic increase. And if we are not sure where the decadal increase is positive or negative, something like that, then we will go for the incremental increase. Okay, so this is how you have to do it, right? I hope this is very simple, but we can expect one question from this. Okay, so let's go to the next problem. It says that a water sample is analyzed for coliform organisms by multiple tube fermentation method, and the results of the confirmed test are as follows. So we have three different sample sizes, and we can see the number of positive tubes and the number of negative tubes out of 5 are mentioned. And the most probable number of the coliform organisms for the above results is to be obtained from the following MPN index. So MPN index table is also given. So where we can see that for the combination of different positive tubes, the MPN index per 100 ml is mentioned. So what is the MPN of coliform organisms per 100 ml for this particular problem? Okay. So please try to calculate. If you know how to do it, it will take just 2 seconds.
Is it 11?
Sorry, how much?
Is it 11?
No, 11 is not the right answer. I hope you know the theory behind the MPN test. Like, what do we do? Why only 5 tubes values are given? And what do you mean? So, first of all, what do you mean by positive tubes and negative tubes? Any idea what do you mean by positive tubes and negative tubes?
Like if we put these tubes and they have like a certain vessel in it, like if the gas forms, it's positive. If it's not, it's negative.
Yes, yes. So we check the gas formation, and this gas formation is due to the presence of microbes. So ultimately, we are trying to predict how many microbes are there in my system. Okay, and there is one more thing called a sample size. So that much amount of sample we will put, and we will check how much, how many positive tubes and how many negative tubes are there. So let me give you a quick for others to understand. So in MPN test, it's a statistical method. Okay, it's a statistical method. So with the help of some statistical table, we try to predict how many organism microbes are there. So we have three set of test tubes of 5 each. Okay, so in the first 5 test tubes, we will put 10 ml samples, 10 ml of our sample. Okay, in each of the tubes. In the next, we will put 1 ml. Okay, and in the other, we will put zero point 0.1 ml, very less, zero point 0.1 ml. So here it is 10 ml, here it is 1 ml, here it is 0.1 ml. And then with, so we expect that our sample is having some microbes. I don't know how many microbes, but some microbes. So we will put like this. Then for the microbes to grow, we will add some nutrient media. Okay, we will add some nutrient media. So since in the first 5 test tubes we have added more samples, so we will put some more nutrient media. The amount doesn't matter, but we will put double the amount of nutrient media as compared to the other. Then in the other, we will also add some nutrient media, or we will call it as nutrient growth. Okay, nutrient growth. Then what we will do, there is something called as Durham tubes. Okay, Durham tubes, very small tubes like this. So we will invert it and put it in the test tube. Okay, it will look some, suppose this is the enlarged view of a test tube. Okay, this Durham tube will be lying like this in inverted manner. Okay, so now we will do it the incubation for 1 day, 2 day, 3 day, whatever. Okay, we will do the incubation, and due to the presence of microbes, if microbes are present in the system, what will happen? Some gas will be formed. Some gas will be formed and collected in the Durham tube, which you can see. So if gas is formed, then we will tell that it is a positive tube. Okay, it is a positive tube. So now let us see what is happening in this problem. In this problem, instead of 10 ml, 1 ml and 0.1 ml, in the question it is given that we have sample size of 0.01, 0.001 and 0.0001. Okay, so we are adding very low. Okay, so how much times lesser sample we are adding? We are adding 10 divided by 0.01, so it will be 1000. So 1000 times lesser sample we are adding. Okay, and in the question it is found that in the first 5 we have all 5 as positive, in the next 5 we have 3 as positive, and in the next 5 we have 1 as positive. Okay, so if 5 is positive, then 0 will be negative, here 2 will be negative, and here 4 will be negative. Okay, are you understanding what till now? Okay, so that's how we have to do this. Now, once we know the combination of these positive tubes, so here the combination is 5 3 1. Okay, here the combination is 5 3 1. So we will check corresponding to the 5 3 1, what is the value given in the table. Okay, so we have some MPN table. We call it as MPN table. So one side there will be combination like 0 0 0 0 0 0 1 0 0 2. Okay, like that 1 0 0 1 0 1. So like that all the combinations will be given, and corresponding to that some values will be given like 3 4 6 10. Okay, some numbers will be given. So we have to check what number is there for 531. So in the problem itself, they have given the numbers. So for 531, the number is 110. Okay. For 531, the number is 110. But remember, this 110 value is corresponding to 10 ml, 1 ml, and zero point 0.1 ml of sample. Okay, so this table is formed corresponding to always this sample. But we have some different samples. We have some different samples, and we calculated it is 1000 times lesser. Okay, so we have to just multiply 110 into 1000. So the final answer will be 110000. Is it okay? So this is the answer 110. So 110 into 1000. Is there any doubt in this? Please let me know because this is very important. Any doubt in this? Okay, I hope you understand. We have to find out the combination of positive tubes. Take that combination, see what is the formula, what is the value in the MPN table. Take that formula, multiply with the number of dilutions. Okay, so it is the table is always for 10 ml, 1 ml, and 0.1 ml. But instead of that, if the question is given for 0.01, 0.001, and 0.0001, so 1000 time dilution is there. So we multiply the value with 1000. Okay. So that's how you have to do it. Okay. So now instead of, so I hope the previous problem is clear to all of you, right? So now instead of the the MPN table, we can directly calculate the MPN also. Okay, so there is something called as Thomas equation or Thomas equation. Okay, so a standard multiple fermentation test is run on a sample of water from a surface stream. The results of the analysis of the test are given below. Determine the MPN using the Thomas equation. Okay, so here also we have different sample sizes and number of positive tubes out of 5 and number of negative tubes out of 5 are also given. So one thing is that you take, so here 10, 1 and point 0.1, you have the value as 4, 2, 1. So for this combination, check what is given in the MPN table. And there is no need to correct anything because sample size is the same. Okay, so you see for 4, 2, 1 what is the value and report. Otherwise, you can also use Thomas equation. Anyone aware of the Thomas equation? No?
It was number of positive tubes divided by the square root of samples in negative tubes times to all samples
Yes,
in
yes,
all tubes.
yes, yes, yes. That is correct. That is correct. So that is the Thomas equation. So as she rightly told, so first find out number of positive tubes. So we have 4 plus 2 plus 1, that is 7. Then you find out ml or volume of sample in negative tubes. So what were the negative tubes? So we have one negative tube plus three negative tube plus four negative tube plus five negative tube. So this was there. Okay, and how much ml? So for one we have 10 ml, for three we have 1 ml, for four we have zero point 0.1 ml, and for five we have 0.01 ml. So just multiply. We have to find out the volume. Okay, so that much. So this is 13.45 ml. Then ml of sample in all tubes. So here there is no positive negative. Okay. So we have 5 plus 5 plus 5 plus 5. So we have 10 ml, 1 ml, zero point 0.1 ml and 0.01 ml. So if you do that, you will get 55.55. Okay. Now as per Thomas equation, the MPN per 100 ml is given by number of positive tubes into 100 divided by square root of ml of sample in negative tubes into ml of sample in all tubes. In all tubes. Okay, so just put the values. So it will be 7 into 100 divided by root over 13.45 into 55.55. So you'll get around 25.609 or 26, you can say. So 26 per 100 ml. Okay. So mostly this value is close to the value which we see in the MPN table. Okay, it will be almost same, right? Okay. Let's move forward. I hope this is clear to all of you. Match the typical water quality parameters with their respective categories. We have chemical, physical, biochemical, and microbiological. So this is very easy. You can answer. So C, this is very easy. So chemical, we have salinity, hardness, heavy metals. Physical, we have taste and odor and temperature. Biochemical, we have BOD and TOC. And microbiological, we have pathogens, VSS, or other viral particles. So all organisms. Zeta potential is the electric potential between the shear plane and the particle surface. Is it true or false? False. So what should be corrected here?
It's between the shear plane and the bulk solution.
Yes, exactly. So this is false. It is the electric potential between the shear plane and the bulk solution. We have seen the diagram before, right? So the same thing. You can refer to the diagram again, and it is known as the zeta potential. Select the correct characteristics of a coagulant required for coagulation. Non-toxic at working dosage, should be having a high charge density, should be having a low charge density, insoluble in neutral pH range, or soluble in neutral pH range. What should be the correct statement? Or rather statements here, more than one answer are correct. So please try to answer. A and D. Okay. So A, B, D. Yes. So A, B, D is right. So definitely the coagulant should be non-toxic. That is very obvious. Then it should be having a very high charge density, right? Because it has to neutralize. So high charge density should be there, and definitely it should be insoluble. Okay, it should be insoluble. So at neutral pH range. So A, B, D, and are correct. Next. About coagulation theory, the net force on the colloids is repulsive at greater distances and becomes attractive only after passing through maximum net repulsive force, called the energy barrier. The statement above is relevant to which of the following mechanism? So A, it is very obvious because what happens is, suppose two negatively charged particles are there, so they will be repelled, there will be electrostatic repulsion, okay, when they are at greater distance. Only after passing through the maximum net repulsive force they become attractive. When they become close and close to each other, they will become attractive, and this force, maximum net repulsive force, is known as the energy barrier. They have to overcome the energy barrier to become attracted to each other. So this is the statement of ionic clear compression. Okay, so all the explanation is given here. So you can see at greater distances, the net force between two colloidal particles is repulsive due to the electrostatic double layer interaction. Okay, so interaction due to the double layer, it will be repulsive. And this repulsion arises from the overlapping electric double layer surrounding the particles. As the particle moves closer, the repulsive force decreases, reaching a maximum repulsive energy called the energy barrier. Okay, this barrier prevents particles from coming into contact and stabilizes the colloidal system. Beyond the energy barrier, when the particle becomes even closer, the van der Waals attraction forces become dominant. Okay, so they have to overcome the energy barrier for the van der Waals attractive forces to be dominant. Okay, at this stage, the attraction overcomes the repulsion, leading to irreversible aggregation or coagulation. Okay, next. This is a numerical. So we have the following information of a community is given below. present population is 34,000, expected population in 20 years is 52,000, present water consumption is 37 meter cube per day, water treatment plant design capacity is 5600 meter cube per day. Assuming arithmetic rate of population growth, the number of years from now when the plant will reach its design capacity will be. So how many years it will take for the plant to reach its design capacity? Tell me. And it is given that the population is increasing at an arithmetic rate. So arithmetic rate increase means every year, okay, the increase in the population will be the same. Okay, the delta P will be the same. So please work it out. Anyone with the answer? No one got the answer? Any idea how to approach this problem? Anyone? Then we can discuss. So we have present population and the population after 20 years. Okay, so we know in 20 years how much it is going to increase. So we can, so since it is given as arithmetic rate of population growth, so we can see each year how much it will increase. Right, we know the starting point, we know the end point. We can find out at each year how much it will increase. Also, we know that present capacity and the design capacity. So we can find out how much more it can accommodate. Okay, then find out what is the requirement, present requirement, how much water is required per person. Okay, and each year how much this requirement will increase. Then we have to just divide it. Okay, so let's see. So this is question number 13. So first calculate what is the average increase in population per year. So we have, so let's say as X bar. So we have, ultimately we have 52,000 population. Present population is 34,000 and it is over a period of 20 years. Okay, so average increase is 900 per year. So 900 per year it is increasing. Now how much capacity it can be increased. So design discharge to reach maximum capacity. Okay, so mac 1 minute. Yeah, so maximum design capacity is 5600, present is 3700. Okay, meter cube per day. So we have 1900 meter cube per day we can increase. Okay, this much we can increase. Now what is the present average water consumption? Average water consumption per person per day. So that is equal to, we have 3700 meter cube per day, and there are 34,000 people. 34,000 people. So we need 0.1088 meter cube per person per day. Okay. So what will be the increase in consumption per year? So if 0.1 meter cube per day is required per person, so what will be the increase in consumption of water per year? Per year 900 people are increasing. So in a year 0.01088 into 900. So we need this much meter cube per day more. This much meter cube per day we need more. Okay. So now the final thing, we can go only up to 1900. Okay, and this much is increasing per day. So how much time do we have? We have number of years to reach capacity is 1900 by 97.92. It is 92. Okay, so this is 19.4 years. Okay, this is very simple. Just find out how much population is increasing per year, how much increase we can afford till we reach the design capacity, what is the per day per person requirement for 1 year, how much will be required, then just divide. Okay, the difference and the per year consumption. So 19.4 years. Next, compute the fire demand for a city of 1 lakh population using the formula of America Insurance Association, or also known as National Board of Fire Underwriters formula commonly. The fire demand is. What is the fire demand? Just a one line answer. Please let me know. I hope you are aware of the formula. No, I think this is, what is the unit?
Is population in thousands, or is the population P in thousands, or how is it?
Yeah,
Like
so
before?
here also we have to take the population in thousands.
Okay.
Yes, this is correct. This is correct. So, how did we get this? So, the formula is Q is equal to 4637 root P into 1 minus 0.01 root P. So, here also P is in thousands. Okay. But one more thing you have to keep in mind. Yeah. So, okay. One, I forgot to tell. This is not the wrong answer. Why this is the wrong answer? Any idea? Just see the question again.
Oh, in MLD.
Yes. So always see the question. So whatever you have got is in liter per minute. You
Liters
have
per
to,
minute.
yes, you have to convert into MLD. So be careful with that. Many a times do you will find out the correct answer, but the unit may be different. Okay. So here the Q is in liter per minute, but in the question it is asked in MLD. So my Q will be, because it is 1.5 lakhs, so 150,000. So in MLD, it will be 71.763. So MLD is million liters per day. Okay, you have to find out in million liters per day. Next, if the average daily demand of a city is 150,000 meter cube, the maximum daily consumption in meter cube will be. What will be the maximum daily consumption? Yes, 270,000 is the right, because the daily variation factor is 1.8. So 150,000 into 1.8 will be 270,000 meter cube, or 2,70,000 meter cube. Next, so match the typical water quality parameter with the respective category: aeration, softening, coagulation, filtration. So it is not the water quality parameter; it is the treatment unit with their function. Okay, tell me the right answer. Yes, C the correct is the correct answer. because for aeration, it is to remove the color, odor, and the taste. Softening we do for hardness. Coagulation is for the suspended matters, and filtration is for the colloidal dissolved or the bacteria. Okay, so C is the correct answer. Select the correct statements regarding coagulation. Alum coagulation produces aluminum hydroxide floc in the flocculation process. Alum coagulation decreases pH in water. The zeta potential of the particle is increased during coagulation. The correct sequence of treatment of a typical turbid surface water is coagulation, flocculation, sedimentation, filtration. Which one of them is correct? A and D. Any other answer? Any other answer? So A and D are correct because it will produce aluminum hydroxide floc, and the sequence of the turbid water is treatment of turbid water is coagulation, flocculation, sedimentation, and filtration. But what about B? Is B correct? Will it increase the pH or decrease the pH?
Increase.
How it will increase the pH? So when we add alum, what is the formula? Do you know? Like, so in the formula, there will be something H plus will be coming out, right? Alum coagulation, that equation. So that will decrease the pH. Okay. So B is also correct. But C is not correct because the zeta potential of the particle is decreased during the coagulation, not increased. Okay. So here another small conceptual problem. Match the following points marked on the graph with the concentration given below with respect to the effect of concentration on electrical double layer. So we have different concentration as 1, 2, 3. Okay, so 660 and 6000 milligram per liter of NaCl. So you have to identify, okay, what kind of curve will be formed for the potential versus distance. So just one thing you have to understand here is, like, if you add more uh, coagulant or NaCl, the suppression will be more. Okay, so the potential will be much more in the high potential will be much more in the closer distance. Okay, so that's why for 6000 milligram per liter, the curve will be C because it is much more closer. Then we will have 600, so it is for B, and then we have 60. Okay, just see the closeness to the highest potential. Okay, more the concentration, more closer. Okay, so option C is correct. In a water treatment plant, the optimum time of flocculation is usually 30 minutes. In case the time is increased beyond this value, the flocks will, what will happen to the flocks? become heavy and settle down in flocculation, break up and defeat the purpose of flocculation, stick to paddles, or no change. It will definitely break up and defeat the purpose of flocculation. Okay, so option B is correct. Next, a certain water needs 12 ppm alum dosing. The amount of alum needed for 10 mld of water per day is, so amount of alum needed for 10 mld of water per day. Please calculate. B. Yes, B is the correct answer because 12 ppm means nothing but 12 milligram per liter. So 12 milligram per liter into 10 mld. That is 10 into 10 to the power 6 liters per day. So we will get something in milligrams. So convert into kg. It will be 120 kg per day. So just multiplication, nothing else. So 120 kg per day. Select the correct statement regarding turbidity. Turbidity increases the disinfection efficiency of UV method. Maximum permissible limit of turbidity is 15 NTU. Clay, silt, and finely divided particles cause turbidity. Turbidity is the measure of ability to scatter light. So this is regarding turbidity. So yes, C and D are correct because turbidity will not increase the efficiency of disinfection. We know turbidity acts as some quencher. Okay, it will kind of protect the microorganisms from the UV disinfection. Then the maximum, what is the maximum permissible limit of turbidity?
5 NTU.
5 NTU. Okay, and C and D are correct. Okay. Quality parameters of rainwater from different sources are given below. Water drawn from which of the above sources can be acceptable for drinking without any treatment? Okay. So characteristics of water is given. You have to find out which of the sources is acceptable without any treatment.
A.
A. Yes. A is the correct answer. So for pH, we know that the value should be in between 6.5 to 8.5. Turbidity should be less than 5 NTU if there is no alternate sources. Otherwise, it should be 1 NTU. TDS, it should be less than 500, but in case no other source is available, then 2000. For chloride, it is 250 and 1000. Okay, in case of no alternate source, it is 1000. For fluoride, it should be 1 to 1.5. Okay, in case of no alternate source, it should be 1.5. So option A is the right answer. Okay, another numerical. 40 mld of water is being treated with 18 milligram per liter of alum in a water treatment plant. Calculate the yearly alum requirement. If the water contains 5 milligram per liter as CaCO3 of alkalinity, calculate the amount of CaO of 85% purity required. So try to solve this. I'll wait for some time. It's a subjective problem, so it will take some time, but please try. Then we will discuss how to solve this. So here what is happening is uh, we have a we have a reactor where some 40 mld of discharge is coming, and we are adding alum. Okay, we are adding alum of 18 milligram per liter, and in the system there is already 5 milligram per liter of alkalinity as CaCO3. It's already there because alum will react with alkalinity. Okay, it will react with alkalinity. So first let us find out the quantity of alum required. So quantity of alum required, so it will be 18 milligram per liter into 40 mld. Okay, so 40 into 10 to the power 6 into 365 days. Okay, and we will convert in tons just to make it a smaller value. Okay, so we will convert in tons. So the alum required will be 262.8 tons per year. This unit can be anything. Okay, just you have to multiply with the discharge. You can keep it in liters per day or whatever, like milligram per day or tons per year, like that. Anything you can keep. But this is a perfect way to report the value 262 tons per year. Now coming to the next part, how much of CaO will be required. So first we have to find out how much extra alkalinity is required. Okay, the water has already 5 milligram per liter of alkalinity. Okay, so always you should know that 1 gram of alum reacts with how much milligram of how much gram of alkalinity, any idea? 1 gram of alum will react with any idea? So this is found stoichiometrically. So this is 0.45 gram of alkalinity as CaCO3. Always remember it is as CaCO3. Okay. So for 18 milligram per liter of alum, it will react with 18 into 0.45, or we can write 8.1 milligram per liter of alkalinity as CaCO3. Now 5 milligram is per liter is already there. So additional requirement will be 8.1 minus 5. So 3.1 milligram per liter. So that much we have to add as CaO. Okay, as CaO. So what happens when we add CaO with water? It will give CaOH thrice, and it will again give some CaCO3. Okay, so 1 mole of CaO will give 1 mole of CaOH thrice, will give 1 mole of CaCO3. Okay, it's all the same. Okay, so that means 1 mole of CaCO3 corresponds to 1 mole of 100% pure CaO. Okay, so for 3.1 milligram per liter of CaCO3, how much CaO is required? Any idea? How do we calculate this? We calculate, right? 3.1 milligram per liter. So for 3.1 milligram per liter of CaCO3, how much CaO is required?
We can multiply by 3.1.
Yes, okay, 3.1. but still it is in milligram per liter, the other thing is in mole. So first we have to convert. So for what is the unit weight of CaCO3? It is 100, right? 100 grams. And for CaO it is 56 grams. So multiply by 56 by 100, right? Because 1 mole of CaCO3 means 56 gram of CaCO3 will correspond to 100 grams of, sorry, 100 grams of CaCO3 will correspond to 56 gram of CO. So 3.1 milligram of CaCO3 will correspond to 3.1 into 56 by 100. Okay, so it will be some value, let it be. And this is for 100% pure CO, right? This is for 100% pure CO. So ultimately for 85% pure CO, quantity required will be quantity required will be 56 by 100 into 3.1, right, into 1 by 0.85, because it is 85% pure. So you have to just divide by 85% into the discharge, 40 into 10 to the power 6, okay, into 365 to convert into year, into for tons 0.10 to the power 9. So you'll get 29.8 tons per year. So that's how you have to do it. Is this clear to all of you? Any doubt in this? Okay, I hope this is clear. Any doubt you can ask me. Okay. So for if purity percentage is given, just divide it. So these are the answers. Okay, so one more problem is there, but it's just related to some unit conversion. It looks a very big problem, but we are not solving this right now. I will just tell you the approach. Okay, you can try it out in your free time, and if you have any queries, so this is an extra problem. Okay, but it will clear your concept. So that's why I have given you. So you can try it out. If you have any queries, you can send an email to me, right? So it says that a chemical supplier reports the concentration of stock alum as 8.37% as Al2O3 with a specific gravity of 3.1.32. Okay, so for the stock chemical, we have to calculate what is the molarity of Al3 plus and the alum concentration if reported as Al2SO4 thrice dot 14H2O. Okay, so these are very practical problems because we always make some stock solution, okay, of some percentage, and then from that stock solution, whatever concentration is required, we will convert. Okay, so you should be comfortable of changing the units as per the formula or as per the uh, way it is given. So sometimes alum may be represented as Al2O3, sometimes it may be represented as Al3 plus, sometimes it will be represented as Al2SO4 thrice dot 14H2O. Okay, so I will, for your help, I will solve the first two problems. The next four you can try it out and send me by email. If you are not able to solve, just drop a mail. I will give you the solution, or maybe we will solve in the next class. Okay. So for the first two problems, let's see. So suppose Al2O3 is, it is given in the form of Al2O3. So what is Al2O3? What is the mass? Okay, weight. So it is 2 into 27 plus 3 into 16. So it is 102 gram per mole. So first question, what is the molarity of Al3 plus in the stock solution, right? Molarity. What is the density of the stock solution? Density was given as 1.32 kg per liter. Okay, so first we will find out what is the concentration of alum in stock as milligram per liter. Okay, we will find out in milligram per liter. So, and the percentage of the stock is 9.58 percentage is given in the problem. Okay, so my C stock will be 9.58 by 100. Okay, because 9.58% into the density 1.32 kg per liter into the density of water. So 1000 gram, or no, we have to just convert into the uh, gram to kg because it is given in kg. So we are just convert into gram to kg. So it will be 126.456 gram per liter of Al2O3. Okay. So generally the density is 1.32 kg per liter, but it is only 9.58% solution. So we'll just multiply it and we will get the value. Okay, so that's how we will report. Now, what is the molar concentration? Molar concentration of Al3 plus, because this is for Al2O3, right? So for Al3 plus, it will be 126.456, okay, gram per liter as Al2O3. Now for now for each Al2O3, what is the gram? So 102 gram of Al2O3 we have to divide it, because 1 mole of Al2O3 will have 102 gram of Al2O3. Okay. And then for each mole of Al2O3, we have 2 moles of Al3 plus, right? So Al2, we have 2 moles of Al3 plus. So we will multiply with 2. So this will be 2.497 mole per liter or 2.497 ml. Okay, so practically we will sometimes many times report like this, either in terms of Al3 plus or Al2O3. Now let's see how to report in terms of alum, like Al2SO4 thrice the 14H2O. So we will calculate the molar mass first. So molar mass of Al2SO4 thrice dot 14H2O. So it will be 2 into 27 plus 3 into 32 plus 26 into 16 plus 28 into 1. Okay, it is 594, right? So here again C stock in terms of alum, it will be, we know 126.456 gram per liter of Al2O3 divided by the molecular weight of Al2O3, okay, into 594 gram per mole of alum. So this will be equal to 736.42 gram per liter of alum. So in various ways we can report the concentrations of alum. Okay. So that's how we have to do it, right? So you please take a screenshot of this problem, try the other parts. If you are not able to solve, let me know. We will discuss it in the next class, or I can send you the correct solution. Okay, please try it out, right? I hope you have taken the screenshot. So that's all for today. Okay, that's all for today. We will meet again in the next class on 17th March, same time on Tuesday, 7 to 9 p.m. And if you have any queries, you can reach out to me at saha19akash at the rate gmail.com. Okay. So session is over for now. You can leave if you don't have any other queries. Thank you.
Sir, would it be possible to change the time to 6:30 just for the next Tuesday?
But actually, this has already been like what time do you want?
6:30 IST.
Sorry, 6 to 8,
No, 6:30.
6:30,
Um, oh, sorry, it is 7 according to your time, so it's 7:30.
7:30. Okay.
Yeah.
Okay. I'm not sure if we can do. I will. check with the NPTEL team. Okay, if possible,
Yeah, I just need it for just for the next Tuesday.
just for the
Just
next.
1 week.
Okay,
Yeah.
okay, we'll try it out. Otherwise, you go back to the YouTube video which we are uploading. Okay.
Okay.